The first thing we're going to do in this video is finally fix the stickiness of our player's physics. Whenever we jump and land on the ground, there is a stutter that happens in the movement. This is because the player has a small amount of friction applied to their collider by default. Let's make a materials folder in our assets, and then we'll create a new physics material 2D that we'll call player. All we need to do is change the friction value for this material to 0. In the Unity documentation, it says that a physics material applied to the rigid body will affect all of the attached colliders if they do not have their own material attached. But I've found that simply attaching the material to the rigid body doesn't override the default friction on the player's box collider. So we are going to assign our player material to both the rigid body and the collider just to make sure that the friction is eliminated entirely. And that's all we need to do in order to fix this problem. If we run the application now, the player will be able to jump around and run without getting stuck on the ground. To set the stage for testing out the hang action, let's add some more surfaces to our level. Place some solid tiles 4 spaces above the ground. This will be just the right height for the player to jump up and grab with the new hang ability. We'll get started by creating a new script in our player states folder called hang state. As we've done before, we'll inherit from the player state base class, and then we'll ask Visual Studio to implement the constructor so that it passes its arguments onto the base class constructor. Let's now include a hang value in our player state type E09, and while we're at it, we'll just include all of the values we'll eventually use so that we don't have to keep coming back to this file. We will also need the climb ledge and wall slide values. We will also go back to the player script and instantiate a new hang state to include in our player's state dictionary. Now we're ready to start building the hang state. Let's include the init method for the state. We will begin by playing the hang animation, then we will set the velocity to 0. Remember, this also zeroes out the damping velocity now, and then finally we will turn off the gravity by setting the scale to 0. Now we are going to extend our trigger info component so that the player can sense when they are able to hang on a nearby ledge. We are going to include 3 separate wall triggers that will help us make this check, and they will also be used for the wall slide action we'll be building in a later video. This first image shows how we will define our new wall trigger collision checks. One of the first things you might notice is that they will have to be flipped to the other side based on the player's facing property. The wall low trigger will not be used for ledge detection, but it will be used to determine whether the player is able to slide down a wall. This next image shows an example of the ledge condition we are going to use to determine if the player is able to grab a ledge. As you can see, the wall mid trigger has just begun to make contact with the upper left corner of the solid tile, but the wall top trigger is not colliding with any tiles. This is the condition we will call ledge. This means that the player is right next to a solid tile, and there is also open space above the tile so the player can grab the ledge and potentially climb up. Notice that if the player was a little bit lower, then both the top and mid triggers would be colliding, and we will consider that to mean the player is too far below the ledge to reach up and grab it. And if the player was a little bit higher up, then the mid trigger would not be colliding, and we will consider the player too high above the ledge to reach out and grab it. Now let's move over to the trigger info component so we can begin implementing these triggers. We'll start by creating the Boolean property called ledge that represents the overall condition we've just described for when the player is able to grab a ledge. This will be if the top trigger is null and the mid trigger is colliding. Let's reorganize this script so that all of the offsets are together in one place. Then we can define 3 new offsets for the top, middle, and bottom wall triggers that we're going to create. After we do that, let's copy the climb bounds variable and property and paste it 3 times to begin creating the wall bounds objects. The most important thing to notice here is that we are going to use the player's scale value to correctly set the horizontal offset based on which direction the player is facing. There is a static method called scale in the vector3 class that multiplies each component of two vectors to create a new vector. We can use this method to multiply the player's scale by the wall trigger offsets. We only ever change the x component of our player's scale, so the only effect of this method will be to either multiply the x value of our vector by -1 or +1. This is exactly what we want. If the player is facing to the left, then our wall trigger offset will be multiplied by -1, and this will flip it over to the left so that it matches the player's facing direction. Let's look back at the wall trigger screenshot again to get a sense of what the offsets should be before we define them. We just described how we are going to use the player's scale to horizontally offset the triggers to the right or left by a small value. This value will be the same for all three triggers. The only difference will be whether it is multiplied by -1 or +1 before it is applied to the player's position. But the vertical offsets will be different for each trigger. The simplest way to think of these is going to be as a percentage of the player's height. Remember, the player's position is defined by its pivot point, which we set as the bottom center of the sprite. So that is our starting point for determining the offsets. Then we're going to add a percentage of the player's vertical size to place each trigger at the right height. For example, the top trigger is slightly above the player's head, so this offset will be 110% of the player's height, or 1.1 times the y component of the player's bounds. Let's return to the trigger info component to define these offsets in the start method. As we said, the x offset will be the same for all three triggers. The extents of a bounds object is equal to half of the total size, so we are setting the x offset to be a little bit beyond the edge of the player's bounds. And, just to reiterate, this value will sometimes be multiplied by -1 if we need to move the triggers to the left side when the player is facing left. And we will set the y offset to be 10% of the player's height for the low trigger, 80% for the mid trigger, and 110% for the top trigger. Now let's create a new setting that defines the size of each of these wall triggers. We will define a vector2 called wall trigger size, and then we can use this to instantiate each of the wall trigger bounds with the correct size. We aren't going to bother setting the position for our triggers in the start method because they will always be updated correctly whenever their property is requested through the getters we defined. That completes all of the setup we needed to do in the trigger info component for the new wall triggers. Now we can move to the player state class and define a method called update wall triggers that will run these collision checks whenever we need them. The only real difference here is that we're going to run multiple checks with one method, but the pattern we're following is exactly the same. We'll make use of the three bounds properties we just defined, and then we'll be sure to filter these collision checks using the surface layer mask. Then we'll call this new method in update triggers. The last thing we'll do before we test this out is to draw these collision checks to the screen using our onDrawGizmos method in the player class. We do this exactly the same way we drew the ground and climb checks. If we run the application now, we should be able to move the player in the scene view to make sure that these triggers are all firing correctly. It looks like our wall triggers are responding exactly how we wanted them to. That means we can actually begin building the hang state action using this new trigger information. Let's first go into the move state to define the condition where we will transition into the hang state. We can add a new if statement to our series in update that will check to see if the player is entering an up input value while their ledge trigger property is also true. If this is the case, then we can transition them into the hang state. If we test this out, we can see that it is already kind of working. The main problem is that the player freezes in place wherever they were when the condition was true. But what we really want them to do is snap to the correct hanging position when they enter the state. In order to do this, we will define a new setting called hang offset that will determine where they should hang relative to the ledge corner that they just grabbed onto. We'll look at one more screenshot to get a sense of what this hang offset really is. Here the player's position is marked at the bottom, and the ledge position is marked at the top to help orient us. The hang offset vector is going to have the x component displayed in yellow and the y component displayed in red. So we're going to move the player down y units from the ledge position and then left x units from the ledge position. Although keep in mind we will also need to use the scale trick here because the horizontal offset will be in the other direction when the player hangs from a ledge while facing to the left. So let's define the hang offset in our settings with a negative x and y component. This will be the default hang offset we use when the player grabs a ledge from the right. Then we'll multiply the x value by -1 whenever they grab a ledge from the left, using the scale function just like we did with the wall trigger offsets. Now let's finish writing the init method for the hang state. We have one more issue we need to address. We need to know what the ledge position is when we try to grab it. We will use a bit of a trick to find this position. We basically know that the middle wall trigger will be very close to any ledge we are trying to grab because of the way we've defined our ledge property. So it turns out that if we simply take the center of the middle trigger and round its values to the nearest integer, we will get exactly the position we are looking for. You might need to look at the tile map and play around with the sprite for a little while to see this, like I did, but you'll eventually see that it always gives us exactly what we're looking for. Now that we have the ledge position, we can combine this with the hang offset setting in order to snap the player to the exact position we want them to hang from. We will use the player's set position method to place them at the right hang position, and we'll make sure to use our scale trick to ensure that the direction the player is facing is accounted for when setting their position. The only thing we have left to do is to make sure our player can exit the hang state so they don't get stuck hanging on a ledge. We can introduce the set vertical input method to do this. We will make it so that if the player enters a down input when they are hanging, they will be put back into the move state, which will turn back on gravity and cause them to begin falling from the ledge. We can now run the application and test everything out. You should be able to jump up and grab the ledge by holding the up input, and then you should also be able to drop from the ledge by pressing down. This completes our hang state action. Also take a second to notice that we can see our current player state being displayed in the inspector under the player script section. In the next video, we'll introduce another new state that will allow the player to climb up to the surface they are hanging from.